Hello, my name is Frias, and in this short video, I would like to introduce you to our paper in which we analyze how spectrum affect mobile network deployments using empirical analysis based on crowdsourced big data.
Over the last decade, mobile wireless networks have experienced unprecedented growth rates in traffic demand. Expanding network capacity has historically been addressed via three network expansion techniques. First, using more advanced technologies with higher spectral efficiencies. Second, densifying the networks, that means deploying more cells. And finally, increasing available spectrum for mobile in both higher and lower bands. The extent to which operators rely on new spectrum integration or network densification to expand their network capacity depends on several factors, such as market share, spectrum portfolio, or passive infrastructure sharing agreements. So, over time, operators have increased their bandwidth as new bands have been allocated to mobile. But it turns out that the properties of the mobile bands are different, as not all frequencies propagate equally. Therefore, the frequency bands for 4G networks have ranged from 800 MHz to 2600 MHz in Europe. This frequency diversity will continue to increase with the new generation of mobile networks, 5G, for which new bands have been allocated in low and mid spectrum as well as in the range of millimeter waves.
So the objective of this paper is to understand the capacity expansion strategies of the mobile network operators in the deployment of 4G networks, paying special attention to the use that they make of the different frequency bands.
Specifically, we address the following research questions. How is either low or high frequency spectrum used in 4G mobile networks in urban areas? To what extent are they complementary? Second, we look at the factors that affect how mobile network operators, MNOs, use either low or high frequency spectrum, particularly how the use of the frequency bands relate to the E-node B density and available bandwidth. And finally, we look at how frequency affects user received power and received signal quality.
To provide answers to these research questions, we have developed a method that draws on crowdsourced measurements, that is, on massive data provided by users through mobile applications.
The method computes a node B density by type of node, that means by all possible combination of frequency bands, and computes also reference signal received power, RSRP, and reference signal received quality, RSRQ, by frequency band. For these, we use, in addition to the RSRP and RSRQ values of the measurements, the EU Trans-Cell Global Identifier of the cell serving the connection and the coordinates of the measurement. Additionally, we also use a statistical geographic information from the area to be analyzed. In this paper, we apply this method to the area of Greater London using a dataset with mobile network records across the entire UK. This dataset was provided by a popular mobile app. For the area of Greater London, we have processed over 15 million measurements collected in February 2017.
So the fraction of sites that fully used the spectrum that was available to the mobile network operator ranged from 2.3% to 20%, depending on the operator, and that for the case of most densely populated areas.
Analyzing the resulting node bit density for several operators in Greater London, as illustrated in these graphs, we found that operators with large bandwidth use 42% fewer sites on average in dense urban environments. This difference decreases in suburban areas to 23% fewer sites. Additionally, we found that lower frequencies report lower RSRP values because they are used for cell edge connections, as it is illustrated in these examples, where the purple line representing 800 MHz exhibits the lowest RSRP values. RSRQ values have been found to be lower in the bands used to provide broad coverage, which are 800 megahertz, like in the left-hand side example, and 1800 megahertz, like in the right-hand side example. This is because of the higher interference caused by neighboring cells. Finally, large bandwidth, typically high frequency, improves RSRQ as it allows for fewer users per megahertz, which reduces interference and enables larger cell size.
So, to sum up, our results suggest that in urban environments, available bandwidth rather than propagation properties can determine the preferred frequency band for the deployments by the mobile network operators. This contrasts with the theoretical expectation that high frequencies require more node-based than low frequencies because of the poor propagation properties. Our analysis suggests that in reality, this assumption is more than nuanced. So thanks for watching, and I hope you find the article interesting.